In order to talk about inverse variation, we have to start by going back and reviewing something we did when we discussed linear equations. So we talked about a special type of linear equation called direct variation. Most of our linear equations were y equals mx plus b, but direct variation was the equation y equals kx. K in essence worked like your slope, but we called it something different. We called it the constant of variation. And the other thing about direct variation is that the y-intercept was 0. So the graph of direct variation always passed through the origin, whether the line went up from left to right or down from left to right. It always passed through the origin. We could find the constant of variation by solving this equation for k, and we found out that k is equal to y over x. So if you know some ordered pairs that lie on some curve, you can find the constant of variation by dividing the y values by their corresponding x values. But in order for it to be direct variation, all the values y divided by k must be the same. So now we introduce this new type of variation called inverse variation. Inverse variation is the equation y equals k over x. So it's a little bit different from direct variation. In direct variation, as one quantity went up, the other quantity went up. So as the x values increased, the y values increased. As the x values decreased, the y values decreased. For inverse variation, whose general run-of-the-mill graph looks like this, as x increases, the y values are decreasing because they're going down. As x is decreasing, as we get more negative, the y values are actually going up. So in inverse variation, while one quantity is going in one direction, the other quantity is going in the other. We can find the constant of variation by multiplying both sides of this equation by x. So we find out that for inverse variation, the constant of variation can be found by multiplying x and y. So for direct variation, you would do the quotient of y and x. For inverse variation, you do the product. So let's do a problem where we're going to determine whether a table of data is direct variation, inverse variation, or possibly neither. And I'm also going to discuss how you can graph an equation or graph points on a calculator and determine which type of variation it might be. In problem 1, I'm given this table of data, 215, 4, 7.5, 10.3, and 15.2. And we want to determine if the relationship between the variables is direct variation, inverse variation, or neither. If it is direct or inverse variation, we want to write a function to model it. So first of all, what I want you to notice is as x gets more positive, as x gets bigger, look at what's happening to the y values. They're getting smaller, aren't they? So my inclination would be that it's inverse variation. If it's inverse variation, then all of my products are going to be the same. So 2 times 15, which is 30, better be the same as 4 times 7.5, which happens to be 30. 10 times 3 is also 30, and 15 times 2 is 30. Since all the products are the same, then this must be inverse variation. Here's the third way that you can go and check to see if it's inverse variation. By the way, don't just look at a table and go, oh, x is going up and y is going down, so therefore it must be inverse. Because that could still happen, even if it's not inverse variation. That's why we check k. However, another thing we can do is we can graph this table in our calculator. If you go under Stat and Edit, and you put x into L1 and y into L2. Once you've done that, then you want to go to second y equals. That's stat plot. And under stat plot, you want to make sure it's on. And you also want to make sure that you have, I don't know what it looks like. It might look like this. This type of graph is the one that's highlighted. After you do that, the last thing you're going to do is you're going to go to the zoom button and you're going to look for a function called zoom stat. And when you do that and hit graph, you have a curve on your calculator that looks something like this. I guess they're like little circles. Since this graph is curving downward, this is what inverse variation looks like, because remember I said direct variation is a straight line. Inverse variation has these two curvy shapes that we'll talk more about in the next section. So this must be inverse variation. Alright, so now that I know it's inverse variation, then I want to write the equation. The equation is y equals k divided by x. Well, we found k. K was 30, so the equation is y equals 30 over x. If you go plug that into y1 equals, that curve should lie on top of these points. And that's how you'll know that you probably did the problem correctly. Let's try another one. This table has the ordered pairs 2, 10, 4, 8, 10, 3, 15, 1.5. So if you go and put this into the calculator, so put this into L1, put this into L2, and then do your stat plot, you end up with a curve that looks similar to this. It seems as if it might be inverse variation, because it's not quite a straight line. But in order to check if it's actually inverse variation, you need to check all your products. If all your products are the same, then it must be inverse variation. So 2 times 10 is 20, 4 times 8 is 32, 10 times 3 is 30, and 15 times 1.5 is 22.5. Well, they're not all the same. And then if you try to do the quotients, if it were possibly direct variation, maybe it was a straight line, I don't know. Well, it shouldn't be direct variation, because in order to be direct variation, the graph has to pass through the origin. This graph's not going to pass through the origin. However, I could show you that you would have 10 over 2, which is 5, and then you'd have 8 over 4, which is 2, right away. 3 over 10 is 3 tenths. 1.5 over 15, they're not equal. So in this case, it turns out that they are neither. Let's try this one last time with this particular table, 2, 6, 4, 12, 10, 30, 15, 45. So the first thing that I want you to notice is that as x increases, y also increases. If they're going the same direction, my gut reaction would be that it is direct variation. Let's go and graph this. So go put this one in L1, put this in L2 under stat, and then your calculator should already be set up. All you need to do is go to zoom and zoom stat, and you should end up with a graph that looks sort of like this. Something to that effect. Well, that seems like it lies on a straight line and that it might pass through the origin, so it looks pretty good. Let's do one last thing to determine if it's direct variation or not. It is direct variation if the quotients of y and x are the same. So 6 divided by 2 is 3, 12 divided by 4 is 3, 30 divided by 10 is 3, and 45 divided by 15 is 3. So it must be direct variation. So if it's direct variation, it follows the equation y equals kx. So y equals 3x. And again, if you graph that in y1 equals, and then hit graph, your line should lie basically on top of those points. And that's how you know you probably did it correctly. How about I give you a problem where I tell you the type of variation, and we want to determine the equation and the graph that represents this data and make a prediction about another value. Suppose x and y vary inversely and x equals 4 when y equals 12. Graph the inverse variation. What is the value of y when x equals 10? So if this is inverse variation, then I know it follows this equation. So in order to find k, we would find the product of x and y. So I'm going to use the ordered pair they gave me. They gave me the ordered pair 4, 12. So I'm going to plug in 4 for x, 12 for y, and I find out it's 48. So I know the equation is y equals 48 over x. I also want to find out what y is when x is 10. So if I plug in 10 for x, I find out that y is 4.8. Well, now I have two ordered pairs that lie on this particular curve. I have 4, 12, and I have 10, 4.8. So that kind of makes sense that as x increased, y decreased. So if you want to graph this now, one of the things you can do is you can graph this equation in your calculator and then just go to the table function to find ordered pairs that lie on the curve. So some of the ordered pairs that lie on this particular curve are, 3, 16 lies on the curve. Let's see, 6, 8, 10, 12, 14, 16. So 3, let's see, that's 2. 3, 16 would be about here. Another ordered pair is 4, 12. We already knew that one. Another ordered pair is 6, 8. Another ordered pair is 8, 6. Another ordered pair is, let's see, we know 10, 4.8, but I don't want to graph that because it has a decimal in it. Another ordered pair is 12, 4, which is probably good enough now. And there's our curve going, oops, not very good, but there's our curve going down. And that's probably what the calculator screen basically looks like.